I believe we ended up right about this area on last Thursday, didn't we? We ended up approximately this week. Well, we looked at that table of little CP and big CP, and we looked and said, okay, why is the CP inversely proportional to the molar mass? It has to do with how many pieces. If you got more pieces, what's that going to cause your specific heat value to do? You have more pieces of stuff. Is it going to increase or decrease with more pieces? Okay, question one. You got more pieces. Like, say for example, don't look at your table. You got a sample of aluminum and a sample of copper. Which one is going to be a bigger atom, the aluminum or the copper? Copper is a bigger atom. Which one will have a higher specific heat capacity? The aluminum, because there's more atoms of aluminum in a 1 gram sample, right, than there is of the copper. So if you have more atoms can accept more energy. Each piece vibrates after it accepts the energy. If you have more pieces can vibrate based on the energy that's contained. All right, so the question then goes to, if I heat equal amounts of water and mercury, which one is going to heat up faster? Add the same amount of heat. What are water and mercury specific heat values? There's water specific heat, which is 4.18. Mercury's is much smaller, 0.14. Holy smokes. It doesn't cost you much at all to heat up mercury, right? It costs you a whole lot to heat up water. So which one would heat up faster if I added the same, if I put them both on a hot plate? Which one would heat up faster, the mercury or the water? Mercury would heat up a whole lot faster than water is. Which one has a greater heat capacity? The water does. It can accept more energy before it changes temperature, which makes sense from the perspective of living in a place like San Diego versus living like a place in Arizona. In Arizona, we're locked in by land, right? We're locked in by land in Arizona. In San Diego, they have the ocean right next to them. In Arizona, this part of the year, we might get up to 80 degrees during the day, we might get down to 40 degrees at night, so there's a range of 40 degrees between day and night in Arizona. We go to San Diego the same time of year, they might get up to 80 degrees during the day, but they only get down to like 72 or 73 at night, so there's like an 8-degree difference there. So it's a 40-degree difference in Arizona, an 8-degree difference in San Diego, and we're all about the same latitude, right? We're all about the same distance from the equator. Why is the range of temperature so much smaller in San Diego than it is here in Arizona? What's happening with the water? It absorbs a lot of heat energy without changing temperature itself, because water is so expensive to change the temperature. It costs you $4.18 to change the temperature of 1 gram of it by 1 degree Celsius. Mercury, on the other hand, only costs you 14 cents to change 1 gram by 1 degree Celsius. So you put a whole bunch of energy in San Diego, and it shines on the land, but it also shines on the water. The water absorbs some of it, doesn't change energy or change temperature. It just absorbs the energy during the day. Then at night, what happens to that energy? It's emitted, right, at night. So it's what they call in engineering and in physics, water is a heat sink, which means it can absorb a lot of energy at one point, it can radiate it back out at another point, and it keeps the temperatures much more moderate. So San Diego and Arizona are all about the same distance from the equator, but San Diego has much more moderate temperatures because you're surrounded by a big lake. So maybe that's why people in Arizona like to live next to a lake, right? The golf courses that have the big lakes. If you're living next to a lake, I would think that the temperature at your home would be more moderate because a lot of the heat energy is absorbed by the water during the day. And at night, that heat energy is let go. I don't know if that's true. Certainly might make for an interesting experiment. All right, so within the context of defining what's happening, is the energy coming in or is the energy going out? You have to first define what your system and your surroundings is, because you have to see, is the system releasing energy, is it absorbing energy, and that will help you define exothermicity or endothermicity. So you did this. You put a hot object into water. So if we say that the heat that was released by what? Who released the heat energy? Well, what was the system in this case? The metal. So the Q went out of the metal. So if we're talking about the metals Q, we would call the metals Q is leaving. It has a negative value. It is exiting the system. All right? If we talk about the Q that went into the water, So the water's Q is positive, right? Because it's going into, the energy is being added to, and that's how I remember it. Energy is being added to the water. So we can define the enthalpy change of each as well. The enthalpy change of the metal versus the enthalpy change of the water. And we know that Q equals MC delta T. When I get this Q, and I put it into my enthalpy value, which is kilojoules per mole, if this value is negative, what value is my delta H going to be? It's also going to be negative. If the value for the Q going into the water is positive, what is my enthalpy for the water going to be? Positive. So my delta H values and my Q values are going to be the same sign. And you have to define system and surroundings in order to figure out what is the sign of that particular issue. So positive means you have to add energy in. It is endothermic. Now you can't think like you did in Chem 130. Chem 130, you did the experiment, you felt the beaker, the beaker got hot, you said, okay, it's endothermic. In Chem 130, you mix things up, you felt the beaker got cold, you said, oh, that's exothermic. That's not how you can think of it in here. That was a much more simplified version. What you have to think about is the system versus the surroundings. Which way is Q going? And then you describe either the exodus of Q or the entrance of Q using the positive or negative values. With this idea in mind, now we're going to graduate. We're going to go from not just talking about something that's very well defined, which is the thermal energy exchange, but now we're going to be talking about energy exchange, which is chemical energy that's stored in bonds, as well as phase change energy. And these are much more difficult concepts in energy to understand. That's why I like to start out with a specific heat lab, because that's very simple. So you got hot metal, cool water. Now we're going to talk about chemical energy, which is a different animal, and you have to define your system and surroundings a little bit differently. All right, so in this particular reaction, you see that you've got some higher energy here and some lower energy, and this is called an energy diagram. Let's look at this in types of notations that you are probably more familiar with. All right. I take this same notation that we just had with that particular chemical reaction. This chemical reaction is actually pretty industrially and environmentally and sustainably important. You take H2O, which is a liquid, and you can break it up into its component pieces. Does anybody know how I would do that? How would I break up H2O into H2 and O2? What process could I use? A lot of people think that if you boil water, that's what happens. That when you boil water in the stove, that it breaks up into hydrogen and oxygen gas. And if that were true, I would definitely never boil water on a gas stove. Right? Because what would happen, if that were true, if that happened when I boiled water, and I worked on a gas stove, what would happen? I'd get some explosions going on because I'd be making hydrogen gas. So that's not what happens. There is another way to do this. Yes? Electrolysis, we call that electrolysis. Now, it's a different kind of electrolysis than some of you might have thought about, like get rid of the hairs on your face, right? Around your body, you have electrolysis, you can do that. This kind of electrolysis, what they do is they actually take, say, a container of water, right? Here's our water. And we put two electrodes in there. We have a positively charged cathode and a negatively charged anode, and we connect those to some power source, okay? So we're putting some power in there and sending negative and positive charges down there. What happens is the water molecules come up to one of these, and at the positively charged cathode, we generate oxygen gas, and at the negatively charged cathode, we generate hydrogen gas. So this process actually works by simply running electrical current through water. It will break it up into hydrogen and oxygen gas. And you can actually see this. There's a thing called a Hoffman apparatus that actually does this for you, and you can see the gases produced. This would be a really dandy way to produce hydrogen gas, which I consider the fuel of the future. Hydrogen gas is the fuel of the future. If the manufacturers of automobiles in Detroit 10 years ago, instead of figuring out how to make more Hummers or bigger Cadillacs or SUVs, instead of doing that, had figured out how to make cars powered by hydrogen, and not only cars powered by hydrogen, but create a hydrogen economy in the United States. There's a good suggestion for our government at this point, right? We want a hydrogen economy, you gotta have hydrogen refueling stations. Because if you take this hydrogen gas and have a tank of it in your car, all you need is some oxygen gas, which is in the atmosphere, and you can do the reverse of this reaction. You can take the hydrogen gas that's in a tank in your car, combine it with oxygen in the atmosphere, and it will reverse. And all that comes out at the end of your tank is electric water. That's all the byproducts are of this particular chemical reaction. Now, when you burn gasoline or diesel fuel, there's a whole lot of other stuff that goes on when you burn gasoline and diesel fuel, right? You got some greenhouse gases that are always produced: carbon monoxide, carbon dioxide, methane, lots of really bad greenhouse gases. We also have what are called particulates, unburned hydrocarbons that come out. You can see those in like diesel trucks. You see the big black cloud of smoke. Those are little bits of fuel that have been vaporized and now in the atmosphere as unburned hydrocarbons. So we have lots and lots of issues when we burn hydrocarbons. If we take and we simply use electrolysis, and they could, right now, the way that hydrogen gas is produced is a process called coal gasification. They have to use a lot of electrical energy to put into the water to break it up. Then if you have a tank of hydrogen gas, and there are lots of vehicles right now in London, almost all of its public transit runs on hydrogen gas. All the buses, all the taxis, because they have a real big smog problem in London. So they made a law, and everybody that's public transit has to run on hydrogen gas. They take the hydrogen gas, they put it in the tank, they burn it, and all that comes out of the tailpipe is a little drip of water. If we could do that, instead of burning hydrocarbons, we would have a much more sustainable future in mind. So that's something that y'all should be thinking about how to do this. The problem is if we use something like photovoltaics, solar panels like people have on the roofs, you can take the photovoltaic cells, use the energy from the sun, convert it to electricity, put the electricity into electrolysis like this, and then it's a slow process, but it would create hydrogen. What we have to do is figure out a way to make these photovoltaics cheaper. Because right now, some of the electrical conductivity of these photovoltaic panels is made of platinum, which is very expensive. A lot of the other components are also very expensive. So it's very high dollar to use photovoltaics to do this. But if we could figure that out and make hydrogen gas and then put it in our cars and just burn it, it would solve a whole lot of pollution problems. Brian, you had a question. Right. So y'all should take this as a challenge, right? We have a speaker from Google at the beginning of the semester who inspired us, and we're not supposed to ask our students, what do you want to be when you grow up, right? We're supposed to ask our students, what problem do you want to solve? Here's one. This is a good problem, so y'all figure this one out. Okay, back off my sustainability soapbox and on to the problem here. If we're looking at this from an energy perspective, it costs us energy to go in this direction, right? So would the sign of Q or the sign of delta H be positive or negative as I'm going in that direction? I think, do I have to put energy in, or am I getting energy out when I do this? I'm putting it in. So what would that sign be? Positive. I have to add energy in. That's how I remember it. I have to add energy in order for it to go. Now, is this an endothermic or an exothermic process? Endo. It doesn't get colder. So don't think like that like you did in Chem 130. You have to add energy in. All right, conversely, I take this hydrogen fuel, I put it in my car, I combust it. Is energy going in or is energy coming out in this case? Energy's coming out, right? So the sign of my Q and the sign of my delta H are both going to be negative, and this is an exothermic reaction. Right? We can look at this on an energy diagram basis. If you look back at this energy diagram here, it shows that we've got the H2 and the O2 at a higher energy level than the H2O. Let's put that into our equation to make a little bit more sense out of the equation. Right. So if we look at this, we say the water is at a lower energy level, liquid, right? And the H2 and the O2 are at a higher energy level. Okay, so I start out at lower energy, and this is higher energy. Because in this process, it has absorbed Q, right? So it's going from lower energy, you have to add some energy in to higher energy. The reverse process is also true. These are at a higher energy. I'm releasing Q, or energy, as I'm going from these, which have a higher energy, down to lower energy. So that's what this particular type of diagram, and you're going to see this in your textbook, is this energy diagram, where you've got the H2 and the O2 are supposed to be at a higher internal energy, meaning they've stored some energy that's been added to them, versus the water that's at a lower internal energy before you start. All right, so this relates to the first law of thermodynamics. Energy in is energy out. Whatever the quantity is that it took me to change the water into hydrogen and oxygen gas is the same exact Q, the same exact amount of energy as I get when I take that hydrogen and oxygen and I combine them and make water. It's just a difference in sign. That's all it is a difference in sign. So energy in is energy out. So the first one is endo, second one is exo, and we have to define system versus surroundings, in this case, water versus the hydrogen and oxygen gas, exothermicity, endothermicity. So there's our negative and positive values in terms of the equation. All right, so let's look at this particular reaction, the enthalpy of this reaction. Here I've got, looks like I've got some CH4, which is methane gas. I'm adding some O2 to it, and I'm producing some CO2 and some H2O. So what kind of reaction is that? That's a combustion reaction. All right, let's write the combustion reaction here. All right, our combustion reaction. So we have the CH4, which is a gas, plus the O2, also a gas. We're going to show that it can go both ways, right? Energy in, energy out. And what are my products? Those of you that have the PowerPoint in front of you, what's the products on this one? CO2, gas, and H2O. Is that balanced? Carbon, carbon, 4 hydrogens, 2. Let's try that. Now we got the 4 hydrogens. 2 oxygen, 2, 4. I think that balances it, right? All right, so energy in versus energy out. This is what's going on in this particular reaction. If we look back at the PowerPoint and we look at which one is at a higher energy level, which one's at a higher energy level? So these ones are higher. The first two, the reactants, are at a higher energy level than the products. All right, so we could kind of rewrite that to show that what did I say, the reactants were higher? As a gas, plus 2O2 as a gas, are at a higher energy level than CO2 as a gas versus 2 H2Os as a liquid. So what must this process have been if my reactants started out at a higher energy level and end up at a lower energy level? What must have happened to Q? Q was released, right? So somehow Q had to leave the situation. So is this exothermic or endothermic? This is exothermic. What would my delta H sign be if it's exothermic? Negative. Heat is leaving. So the reverse process then would be endothermic. And my delta H would be positive. Makes sense? Look at the delta signs. Delta H for the CH4 and O2 is releasing energy, just like we said. It's a negative delta H value. It's an exothermic reaction as we're going from the reactants to the products. Reverse is true. I take the products and I go back to reactants. It's the same exact value of Q or delta H. It's just a change in the sign. Okay? So that's called the enthalpy of the reaction. That's sum total of all the energies of the reaction. And here's what I want you to think about in terms of what is exothermic versus what is endothermic? All right. Let's make a metaphor. Let's have a metaphor here of this particular reaction. Pretend this is my reaction where I'm starting a bakery. I'm a baker, and I make some mean cupcakes. I want to start a bakery and sell my cupcakes that everyone loves because everybody's telling me how much they love my cupcakes, and if I start a bakery, they're going to come and buy my cupcakes, right? So, to start my bakery, first of all, I got to have a location. Then I got to get some ovens. I got to get some big mixing machines and some bowls, and I got to invest pretty heavily at the outset. I have to put a lot of energy in. So I'm adding a whole bunch of energy into my situation at the beginning of my business, when I start my business, okay? As I start my business, since I'm only selling cupcakes, I'm only selling for $2.50 each, I'm not getting a lot of revenue back, right? Because each cupcake's only $2.50. People have to find out about my cupcake shop. So I'm not getting a lot of energy out, right? So I'm not getting a lot of energy back. So what's my overall enthalpy in this reaction if I have to put a whole lot in and I don't get much back? What would be the sign of my overall enthalpy here? I put a whole lot in and I don't get much back. The overall is going to be positive, right? I'm going to have to put more in than I get back. So if I put $10,000 in and I only sell 10 cupcakes, which is $25. I put $10,000 in, I only get $25 back. I've invested a whole lot of money, so my overall enthalpy is going to be positive, meaning it is endothermic. Conversely, now I've been in business for a while, right? Now I don't have to invest a lot in my materials because I've got my mixing bowls, I've got my mixing machines, I've got my location, so I've already spent that, but now people are going crazy for my cupcakes. They're like, oh my goodness, Lorelei, your cupcakes are awesome. I especially love those red velvet cupcakes with the cream cheese frosting. You know, those are my favorite. So now I'm selling cupcakes like crazy. I don't have to put much energy in. I get a whole lot of energy out. So in this case, my overall delta H is going to be, I'm going to get lots more money back than what I put into the equation. And that's how chemical reactions happen. You have to break some bonds, right? That's going to cost me energy to break those things apart. But then when I put them together in a different way, some of that energy that I had to use to break them up is now going to be stored in bonds. And so the difference between what it cost me to break them up versus what it cost me to put them back together in a different way is what we call Hess's law. Okay? Hess's law has to do with the overall enthalpy change for a particular chemical reaction. All right, so Hess's law is summarized by this expression. This is something that you need to know for the class for sure and for the exam that you have next week. Hess's law says the overall enthalpy of the reaction is equal to, put some algebraic and calculus symbols here. What's that funny E looking thing? Sum. So you're adding up stuff together. So the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants gives me the overall enthalpy for the reaction, right? So it's going to cost me some energy to break those things up. I'm going to get some energy back when they get put together in a different way. The difference between what it costs me and what I get back is the overall enthalpy of the reaction. And it changes by the reaction. It changes on how complex the things are that you have to break up. It also changes on how complex the things are that you're putting back together. So a reaction itself is not necessarily endothermic or exothermic. It's the summation of the enthalpies of what we call formation. At this point, I want you to take out this table of enthalpies of formation that I gave you. Look at this one. This is the first page of Appendix C in the back of my textbook. So label this. You have 3 more pages of these enthalpy values. I only gave you the first one to direct you where to find them. Okay, this is in the back of your book. You will have to use this reference, the 3 pages in the back of your book, in order to do the homework that you need to do for 5B. Okay? Now, when we're looking at this table of values, if we look at the individual values and we look at the columns of information that we have, okay, this column and this column, we're going to let the 152 teacher that you have talk about delta G or entropy. Okay? We're not going to discuss those in this class. What we're interested in this class is the enthalpy column. So those are the 2 columns you're going to be looking at. And let's look at some trends. First of all, you see some numbers in this column, right? We're looking down this numbers. What are the things that stand out here? You look at this set of numbers. Some of the solids are 0. So, okay, these values, what are the units of these values, first of all? Kilojoules per mole. All right. What it's going to cost you per piece, right? Kilojoules per mole is what it's going to cost you in energy per piece to make that thing. So what this is a table of enthalpies of formation, which we abbreviate delta H sub F. That is the enthalpy of formation. That means what kind of energy did the universe have to expend to either create this thing, or was there any energy expended during this creation? So what things have an enthalpy of 0? What didn't cost the universe anything to make? What kind of things is a solid? Very specific types of things. Metals, metal solids generally have enthalpies of 0. Because you're going to find a hunk of metal on the ground, copper. We're going to assume that after the Big Bang happened, that copper was sitting there after the Big Bang, so it didn't cost the universe any energy to make that. So a lot of the metals you'll see in solid state, as they exist at 25 degrees Celsius, have enthalpies of 0. So they just exist. It didn't cost energy, it didn't make energy. What else do you notice is 0? There's some other things that are zeros. Let's not look at bromine liquid. That's one that's kind of an odd one. Let's look at some of the other diatomics, like H2 or Cl2. Here's one, Cl2. What's the enthalpy of chlorine gas? 0. Do we see any other diatomics? F2. Here's another one at the bottom of this paper. Here's F2. What's the enthalpy of formation of F2? 0. Okay, most of the diatomic gases in their standard state at room temperature have enthalpies of 0. They just exist. All right, so we got some things that are 0. We noticed some trends there. What else do you notice about the rest of the numbers? If they're not 0, they're either what? Negative or positive. So the negative ones mean, did it cost me energy to make that, or did I get energy back when I made that thing? What's the negative sign mean? Negative means that energy did what? Left. So the universe got some energy back when I made that thing. If the sign of the enthalpy is positive, what does that mean about what it cost you to make that thing? You had to put some energy in, right? So positive enthalpy of formation means energy had to be added to that thing to make it. Negative enthalpy of formation means that the universe got some energy as a result of that thing getting made. Right? So you got positive and negative values of enthalpy of formation as well as 0 values. All right, let's take this table now and let's plug some numbers in for the enthalpy of formation for this particular reaction. CH4 as a gas plus 2 O2s gives me CO2 as a gas plus 2 H2Os as a liquid. All right, I want to calculate, using this equation, my enthalpy of the reaction. I know that the enthalpy of the reaction is equal to the sum of the individual enthalpies of the products minus the sum of the individual enthalpies of the reactants. All right, so let's look up the individual enthalpies. That's why I gave you guys the table. What's the enthalpy for CH4 as a gas? What is it? Negative 74.8 kilojoules per mole. All right. What's the enthalpy of formation of oxygen gas? 0, right? One of those, that's 0. Does it show it on your table as 0? O2, there we go, good. What about CO2? What's the enthalpy? What does it cost me to make some CO2? What is it? 393.5 kilojoules per mole. And what's my enthalpy of formation for water as a liquid? Do we have that somewhere? Negative 285? All right. Let's plug that into my formula. I got to add up the enthalpies of the products, right? I got to add up the enthalpies of the reactants. So let's do that. Enthalpy of my products. So the overall enthalpy for the reaction is going to be, I'm going to use the brackets to help keep my algebra and my sign straight. I've got a negative 393.5 kilojoules per mole plus, I'm going to put this in parentheses because it's a negative value, plus I got 2 of these being formed. Each is going to give me 285.84 kilojoules per mole. Does everybody see why I did those? Use those numbers. 93.5 comes from my enthalpy of formation of carbon dioxide. Why did I take my enthalpy of formation for water and multiply it by 2? Because I'm making 2 of them, right? So I got to use 2 of them when I'm figuring out my enthalpy. So somebody with a calculator, what's this part all added up together? It should be a very large negative number, right? Because I have a negative number here. And when I add a negative number, in essence, what I'm doing is subtracting it, right? So I add that negative number and that negative number together. So what do I get? A big number, like around 1,000 something, wasn't it? Negative 965.818 kilojoules per mole. Okay, that's that part. Now I have to subtract the enthalpy of the reactants. So here's my enthalpy of the reactants. I've only got one of those CH4s. It's at a negative 74.8 kilojoules per mole. Plus 0. That was easy, right? So now my overall enthalpy of the reaction is going to be the enthalpy of my products, in this case, negative 965.18 kilojoules per mole, minus negative 74.8 kilojoules per mole. Did you see what happened to the signs there, or what's going to happen to the signs? See what happened? Because we started with my original formula, right? The enthalpy of the products minus the enthalpy of the reactants. How much money am I making in my cupcake shop minus how much it costs me to set everything up in my expenses, right? Okay. Here, what's my overall enthalpy of the reaction? So I take that plus the 74.8. Everybody see how the math works out there? That plus 74.8 gives me what number? Negative 8. There's my enthalpy of the reaction using Hess's law and my enthalpy of formation tables. This is not calculus, right? This is not even algebra, really, yet. This is adding and subtracting. Y'all can do that. All right, let's move on. Try some more examples here. So the enthalpy for the reaction. We just did that, or the heat of the reaction. So they're going to ask you one of two things. They'll say, calculate the enthalpy of the reaction, or calculate the heat of the reaction. Either of those would work. All right, let's try another one. Standard enthalpy change for this reaction is 178.1. Now, they're telling you that's the enthalpy for the whole reaction. The whole thing, right? And they say, from the values for the standard enthalpies of formation for calcium oxide, which is this stuff right here, and carbon dioxide, which is this stuff here, calculate the standard enthalpy formation for the calcium carbonate. All right, I'm going to write this equation on a piece of paper so I don't forget it. And you guys take a look at that. And I'm going to set this up as the delta H for the reaction. I know that value. I know that value now is 178.1, right? And I'm going to set that equal to the enthalpy of the products minus the enthalpy of the reactants. Summarizing my formulas here. So we got CaCO3 as a solid, and it decomposes into calcium oxide solid plus carbon dioxide gas. All right, let me switch over to the, there's my Hess's law stuff for this. And they're telling me now that this is the enthalpy of the reaction, right? So here's my product's enthalpy. This is my reactant's enthalpy. So if we set this up, we know that 178.1 kilojoules per mole is equal to the sum of the enthalpies of each of these things. Okay, what's the enthalpy of calcium oxide from Appendix C? Negative. What is it? Thank you. Kilojoules per mole. What's the enthalpy for carbon dioxide? Okay, so I can work that out here. 178.1 kilojoules per mole is equal to, I'm going to sum these up, right? I got negative 635.5. Then in parentheses, plus my negative 393.5 kilojoules per mole. See why I'm putting in parentheses? Keep my negative value straight, because in essence what I'm doing here is I'm adding both of those negative values together to make one big negative value. Minus, this is what I'm finding out, my x, right? Minus x. Isn't that using Hess's law? Products minus reactants. We know the products. We know the overall enthalpy of the reaction. We have to figure out what the enthalpy of this reactant is, which we're going to call X. So somebody with a calculator, what's negative 635.5 minus 393.5? What do I get? What is it? Negative 1029 is their decimal? It's exactly equal. Okay. Kilojoules per mole minus X, right? So now, using a little algebra, how do I solve this? Okay, so I'm going to add 1029 to both sides, right? Actually, I'm going to, yeah, plus 1029. That's going to give me, what's these two things added together? What's 178.1 plus 1029? What is it? But that's equal now to negative x. You guys know in algebra you can't have a negative x, right? What is?
That's if you subtract it from each other, it should be, since you're adding it.
I'm confused.
If you,
that was our positive value. You're going to have to add it to both sides to get that one out of here. So I got a positive, and positive gives me that, right? Okay. So I can't have a negative x, so what do? You divide by a negative x, or divide by negative 1, or multiply by negative 1. So basically, x now is equal to negative 1207.1 kilojoules per mole. Was this an exothermic or an endothermic reaction? Was it exothermic or endothermic? Exothermic. Did the container get hotter or colder? Did it emit heat or absorb heat? It emitted heat. Heat was exiting the system. All right. Is that the number we got? Oh, thank goodness. It's always helpful when it works out well. All right. We We did this calorimetry stuff. You guys are going to do a lot more of this in lab. You indirectly measure the temperature change. You make that assumption that heat loss is heat gained. Let's do this problem real quick. No, don't put your stuff away. You still got 3 minutes of time to pay for it. Still got 3 minutes of time. All right. Let's do this one. All right, so we got a problem with calorimetry. All right, let's write this down. A problem with calorimetry. We got to start with HCl, right, plus NaOH. Both are aqueous solutions. And what's going to be my product here? HCl and NaOH, what am I going to make? Good old water and salt. An aqueous solution. I believe they said we had 50 mils of each of these, right? And it was 1.0 molar solution. All right, I need to figure out the enthalpy of formation in kilojoules per mole. When I add these things together, you know what happens when acids and bases are added together. It's going to get hot or it's going to get cold? It's going to get hot. Is that exothermic or endothermic? Exothermic. Does that mean my delta H is positive or negative? Negative, because heat is exiting the system. So whatever it is going to be a negative value for my delta H, because we know the acids and bases, when you add them together, it gets hot. How can I, and this is exactly what you're doing in lab this week, so make sure you pay special attention. How can I figure out the enthalpy of the reaction in kilojoules per mole? We're talking about the enthalpy of neutralization for HCl. I think that's what they asked. What is the enthalpy for the reaction in terms of kilojoules per mole of HCl? So I want to know the neutralization enthalpy. Well, what do I got that I can get something out of that's either kilojoules or moles? Come on, you guys. You've done this before. You just got to add the pieces together. What do I got that I can get either kilojoules or moles out of? Moles. I can get moles out of something. What can I get moles out of since I'm talking about HCl here? I can get moles of HCl, can't I? How do I get moles of HCl? So I take my volume. So 1, 2, 3, yep, 0.050 liters times 1.0 molar, which gives me 0.050 moles of HCl. All right, well, I got one part of my enthalpy of the reaction. I figure out how many moles of HCl I have because the question asked for the enthalpy of reaction with respect to the HCl. What's the neutralization of the reaction with respect to HCl? All right, what's the formula? What is kilojoules? What's the kilojoule a measure of? Heat. What do we use to abbreviate heat? Q. What's Q equal to? MC delta T. All right. So now we're doing an experiment that's a little different. Now we're not taking a hot hunk of metal, putting it in cooled water. We're taking two aqueous solutions that have particles in them that once they meet are going to react and release some energy. Now, how do I know that this is going to get hot? How do I know this reaction is going to release energy? How do I know that? It's an acid-base reaction, right? So it has to get hot. So my enthalpy is going to release. So my sign of delta H is going to be negative. All right. So what's my M in this case? If I want to calculate Q, right? Because what are the units of Q? Joules. Wouldn't that get me the kilojoules that I need to figure out my enthalpy of the reaction? All right. So what mass would I use here? Not moles. M is mass. What mass would I use? Nope, not convert moles to anything. Think about, okay, let's step back and think of what's happening here. Here's my reaction container, right? I got my liquid water, my aqueous solution. I got little pieces of acid and base now that once they get together, they make a reaction and the Q goes out into everything around them. So what mass would I use? Say that again. Where did the 100 grams come from? That's the whole mass of everything you got available. That's the mass of the water that the Q could go into. Does everybody see where the 100 grams came from? I heard no. Somebody say no, they don't understand where the 100 grams came from? In this case, yes. In this case, it does. 1 gram is 1 mil. So there's my 100 grams. What's my C for water? 4.18 joules per grams degrees Celsius, right? What's my delta T going to be here? Did it tell us that in the problem? I think it did, didn't it? There it is. Hot dog. There's our delta T. What's our delta T? 6.5. So we can plug that in, right? 6.5 degrees Celsius. Somebody with a calculator. What's 100 times 4.18 times 6.5? Q is equal to, say it again, 27.17. And what are my units here? Joules. All right. Is that my answer? Is that my enthalpy? No, that's my Q. That's the $1,000,000. Now I got to tell how many pieces I have that I'm dividing that $1,000,000 into in order to figure out my enthalpy of the reaction. Now let's decide on the sign of Q. Was this an exothermic or endothermic reaction? Exo. So what sign am I going to assign to this value? Negative. It left the situation. So then by virtue of the fact that I have to use Q per mole, right? I have a negative Q that's going to make my delta H negative. So I'm going to take 27.17, and what am I going to do with that? Kilojoules, which is 2.717 kilojoules, right? Oh, you can't see that. I'm sorry. Thank you. All right. So we took our joules, and we want to change to kilojoules, right? Now it's kilojoules. So now I got my kilojoules of energy divided by that's the exact calculation you do in lab this week. Different acid and base, but basically the big picture is the same. What's the answer? Who's got an answer? What's 2.717 divided by 0.05? What is negative? 54.4 kilojoules per mole. 0.34? 0.34 here?
Yes.
Okay. All right. There you go. Practice this stuff. Read chapter 5, practice 5B before you come back on Thursday. You're going to have a quiz on this. You got to know how to do it.